Okay, welcome everyone to the first problem solving session for the second Agda exercise sheet. Yeah, I uploaded it yesterday, so I hope you all had time to look at it. I'm going to share my screen. Okay, so this is the GitHub repo. I hope you can all see it. Yeah, standard disclaimer. If you want to do them, it's probably easiest to pull them from GitHub and then copy paste the code into a local file where you can work. Otherwise, GitHub will complain when you change that file and you pull later. Yeah, so first exercise is going to be about propositions as types. Martin talked about in the last lecture. Then the second one is a bit more about the equality type, and in particular, we want to look at what it looks like for Booleans. And then the last part is something that Martin didn't manage to talk about in this lecture, so I don't think we'll have time to look at that as well. But this is definitely more difficult than all the other exercises, so maybe you can, maybe you want to go back to it later or after this session and give this one a try. But it definitely uses some stuff in Martin's library or handouts. So yeah, this one is a bit tricky, but fun, I'd say. Okay. So where's my Emacs? Yeah. Okay. Can you all see my Emacs? I'll try to monitor the chat somehow, but this is a bit difficult with the settings. Okay, great. Yeah. All right. So this time we're going to use a bit more stuff than the prelude. The decidability stuff is for the last exercise, so I don't think we'll use that, but we're definitely going to use sums, dependent sum types. Okay, so let's start with exercise 1, and it asks us to fill 2 goals. Called curry and uncurry. I don't know if maybe we can get a quick show of hands in the chat. How many people of you have seen something like this in functional programming, for example, in Haskell? Yeah, okay, so we have some people that that are familiar with these concepts. Oh, that's very good. Yeah, cool. So yeah, I want to do this a bit interactively. So yeah, you can just unmute yourself and make suggestions on how to solve these things. So maybe we'll actually start with curry. What would you do here? Anyone?
Well, you would take the function and then take the term of type A and the term of type B and then pair them together and apply it to the function.
Yeah, exactly. So in particular, this function will be first argument. And then, so I don't know if you want to Emacs, if people are new to Emacs, if they want tips with that, but if you want to mark a region, control, and then the space bar. So if I press that, I don't know if you can see it down here. It says mark set. And then if I move the cursor, it will highlight the region and I can copy paste. So this will be our first argument, that function. Call it f. And then we have to Control C, Control L to load. And then we can check what do we have to provide here. Control C, Control comma, something of type function A to B to X. And yeah, so we have to give it another argument, something of type A. Then Control C, Control comma, the goal becomes B to X. So we give it a B. And the goal becomes something of type X. And yeah, what do we do now?
So now we construct a tuple of A and B, no? Oh, sorry,
Yeah.
F, A, and B.
Yeah, but yeah, exactly. So the tuple A and B would be something like A, comma, B. And it's important that you have this space here in Agda. White space sensitive language. So now we can press Control C, Control dot, and we can make this bigger as well. So we have something of this type, and this is with Martin's notation maybe a bit hard to read because it suppresses the first argument. But yeah, this is yeah, this is a tuple of this type, A times B, and then we can apply F to it. Yeah. Control C, Control L to load. Yeah, and we're done. Okay, for the other direction, maybe one remark. Actually, the way it is written here is suggested for easier reading, but actually those parentheses are not needed in Agda. So this will I've checked just as well. And the reason is that the arrow is sort of right associative, or the way it is parsed, if you just have a bunch of arrows, is that it's, yeah, start bracketing from the right, sort of. But then, of course, here you need it, because this is maybe one function. Okay, now the other direction. Again, we give it a function here. So now we see we have to produce something of A times B to X, and we have a F from A to B to X in scope in our context. So we can give it a pair, maybe call it AB for now. And we have to produce something of type X.
Would also unpack the tuple directly in
yeah,
arguments.
Yeah, exactly. So this, now we're a bit stuck actually, because we sort of want to apply AB to F, but we sort of have to get the content sort of this pair in the first and second element. And there are several ways to do it. One way is to just write it out as a pair already. So now we have an A and a B and an F. Another way is with these easy things. Yeah. Another way is to actually use pattern matching. So if we press Control C, Control C, then Agda will do it for us. But yeah, maybe we're not too happy with these names, and we want to rename them. So yeah, it's often easier to just like write them out as pairs right away when you put them to the left of an equal sign. Okay. So yeah, then the goal becomes FAB. Done. And sort of this is for those with a math background, this way of writing is maybe a bit unfamiliar. So they would write, if a function takes two arguments, they would probably write something like f parentheses a comma b. But the more type theoretic way is gets rid of a lot of parentheses and just writes them in sequence.
I just want to note that another thing that could have been done is to take A and B as a single block and do f of pair 1 AB, pair 2 AB.
Yeah, exactly. Very good. Let's try this. We can actually, so now we know we want to apply f, but we have to give it two arguments, one of type A and one of type B. So here we have AB, which is, as you can see down, of A times B. And then if we look at how times was defined, it was a record type with two fields. Maybe we can jump to that. Again, I move the cursor on the time symbol, and then I press meta or alt and dot, and we jump to the definition, and we see, okay, it's defined as a sigma type where sort of the second argument is independent of this x here. But you can jump to the sigma type, and this is again some syntax, fancy syntax. Finally, we get to the definition, a bit bigger. Yeah, so the sigma is a record, and it has two fields, sort of. One is PR1, which is of type A, and the other is of PR2, which is of type B of PR1. But when we have the normal product, like in the goal, in what we have here, then sort of B is independent of whatever we get from A. So PR2 will always be of B, and we can sort of ignore this last part. So we jump back with alt or meta comma all the way to where we were. And then if you want to jump to the next goal, it's Control C, Control F. Yeah. So we can write PR1, and this under the subscript 1 is just as you expected. It's \_ _1. So yeah, just like the last later command. Oh, and Agda is happy. And for the second thing, we do the same, but maybe, I don't know if you have seen this, but for record types, you can also use sort of dot notation. You could also write AB dot PR2, which is the same as PR2 AB. This is maybe, sometimes this is more readable if you have record fields with a dot at the end of your term. Okay, so maybe a few remarks. Jump to definition. In emails, letting dot and back is done, and then comma. And what else do we have? Jump to next goal. Control C, and then Control F. Okay. I think those three are actually very helpful. Agda key bindings. Okay. So one question was that, yeah, what is the meaning of these two terms, uncurry and curry, sort of under the proposition types interpretation? Maybe someone wants to answer that, or is it too easy?
Well, is that if you provide two hypotheses and get a conclusion, you can provide the two hypotheses at once with a conjunction.
Yeah.
Or one at a time, and it's basically the same thing.
Yeah. So this says if A implies that B implies X, then A and B implies X, and this is sort of the other way around, right? Yeah, sort of you can go back and forth between function on a more programming level. You can go back and forth between functions that take two arguments and functions that take pairs of arguments. Sort of. Yeah. This is a very standard and useful trick. Okay.
So I would like to rephrase it. What we've done, we've proved actually in Agda that these two propositions predicates are equivalent, right? We have kind of a mapping between one and the other in both directions, right?
Yeah.
That's what we've done in Agda.
Yeah. Exactly. So if you sort of maybe you can write something like curry uncurry, which tells you that for all A, B, and X, let's be a bit faster here. And there's this symbol Martin uses, which is this guy is \if. So this is sort of by implication or implication in both directions. So this is, yeah, we can, with combining these two, we can sort of prove that this is true if and only if this is true, right? And I guess it's helpful because we're going to need this guy later. We can look at its definition, and its definition is really just figure A if and only if B, if A implies B and B implies A. So when we want to prove this, Control C, Control comma. Okay, we can do Control U, Control C, Control comma, and then it tells us this is some sort of pair type, not in a very readable form. And this is, maybe we should bring this up with Martin, that these goals become very unreadable. But this is some sort of pair type. So what we can do is we can prove this by simplifying the goal Control C, Control R, or refining, what it's called. So the first goal is one of the implications. So this was curry. And the second was uncurry. So yeah, what we have proved is that sort of these two propositions, or like, yeah, if we read them as propositions, are logically equivalent. Okay. Any questions? Oh, that's great. Okay, so the next thing is a little quiz. Maybe I can copy. I have 10 roles to fill, but not all of them will be possible. And maybe we can have a little poll every time. So write in the, like, who thinks, you can write in the chat that this goal is fillable. And if you're unsure, think about what sort of the meaning of this is under propositions as types. And do you think this is a tautology in constructive logic or intuitionistic logic? Maybe some of you are not familiar with that, but if you are, then this can be a helpful intuition for whether sort of this goal is fillable. So who thinks that one is provable? Okay. Look at the chat. Yeah, so there's some yeses. Yeah, indeed. So what this says is that if A and B or C, then A or C and B or C. And another way to think about it is that this is sort of distributivity of or over and from the right. And this is indeed true. So you can do a quick proof. So we have one hypothesis of type A or C, and oh wait, like this. Okay, so we have something of A and B or C, and we need to produce a pair of A or C and B or C. So what we can do is we can pattern match on our term X, because the sum was record a data type, and so if we pattern match, we get the different constructors here. So this is an in left, and then in the in left case, so now X is something of A and B. So we might write X as A, B. And we have to provide a pair, so we can refine and have to give two things. So we have to give something of A or C. But if we look at what we have in the context, well, we have a B and we have an A, and of course the types, but they're not really important. So, well, we can work with that A. So we have something of type A, but we need A or C. And the way we get that, I'm sorry, is an in left. And maybe you guess it in the other case, we have our B, but we need B or C. So this will be in left B. And here, well, the in right will be something of type C. Fine. We have to give A or C, but we have our little c, so this will be in right C. This 1, 2. Right. Okay. Questions about that? No. Great. Okay, let's move on. I try to speed things up a bit so we can look at the rest. Okay, who thinks that 2 is provable?
Let's see.
Yeah, okay. People believe that in general. I can make this quick. If you have any, wait, oh, this is just the same. Ah, well, this is bad, of course. I'm very sorry. I meant to change it here. I wanted to swap the plus and the times. Plus. Okay. Anyone wants to change their opinion about? Yeah. But this is of course still true. This is sort of distributivity the other way around. The proof is sort of the same, so we might be able to skip it. I'm gonna cheat here a bit because I want to move on. Does anyone want to see this proof, or do you believe me? Okay, what if now it gets a bit trickier? What about this guy, number 3? If not A or B, then not A and not B. Yeah, okay, people say yes, exactly. But we can do this one. So the first argument, F, is of type not A or B, and I name it F because if you remember how negation was defined, there's a function into the empty type. So in terms of negations or functions, sort of, I think this is a helpful thing to remember. And then we have to prove something of not A and not B. So this is a pair. We can do Control-C, Control-R, define. So we have to prove something of not A. We can do refine. This gives us, maybe call it an A. So now we have to produce something of the empty type. So we want to sort of apply F to our element A here, and we will get something of the empty type, but this is not quite possible because it takes values in the disjoint union type. But this is not really a problem because we have our constructor in left that will make that we can apply to A, and the right hand side sort of works analogously. The in right. Okay. So let's move on to 4. Who thinks that 4 is provable? No? Yeah. Okay. So some people say it's not provable. So let's think a bit about why this is not provable. It says that if not A and B, then either not A or not B. Yeah, exactly. So the way so constructively, this statement is not provable without law of excluded middle. Yeah, exactly. So it's sort of equivalent actually to a weaker form of law of excluded middle. I haven't checked that, but it looks believable. Yeah. So if we try to naively prove this, we make this guy an argument f, because this will be a function that, so f will produce something of the empty type if we give it two things, something of type A and something of type B. But now the goal type is a union, right? So we have so this has to be in left or in right of something, but which one is it? So we can't decide that because we don't know anything about types A and B here. Yeah, there's no way to choose from what we're given with F if this should be an in left or an in right. Okay, let's move on. Was that satisfying explanation for everyone? Or are there still questions about this? No? Great. Who thinks that 5 is provable? Yeah. Exactly. So 5 is actually a standard result, and this is called, I mean, if you read it out under propositions as types, this is really contraposition, right? If A implies B, then not B implies not A, and this is of course true intuitionistically as well. So we have several arguments. The first one is an F, so this will be from A to B. Then we can give it something G. So G is a function that takes something of type B and gives something of the empty type. So this is not B. And we have to give it a not A, but not A is a function type. So we can give it one more argument, A, and we have to produce something of the empty type. And now if you look at what we have down here, A, G, and F, you can, there's pretty much only one way to go forward. We can apply F to A, then we get something of B, and to that, so we can use this and apply it to G, and we get the desired. Okay, now 6. Yeah, exactly. 6 is not provable without law of excluded middle. This is sort of one of the perks of intuitionistic logic. So we have this direction, but from not A implies not B, we don't get that B implies A. And if you think about it, if we start trying to prove it, so we give it an F and a B. So what do we have? We have a function from not A to not B, and we have something of type B, but we have to give an element of A. So yeah, we sort of have nothing to construct elements of A for an arbitrary A. We know nothing about A, and with our B and our F, we'll just not get there. Okay, everyone on board with that? Yeah. Okay, so yeah, this is something to wrap your head around when you learn intuitionistic logic, maybe. But I think sometimes it actually helps in type theory to see why this is not provable, because you really don't think about, then it helps to not think about it as propositions, but you say, okay, you're giving a function from not A to not B, and you're giving a B, but how are you going to construct something of type A from that, right? It's almost easier to understand that this is not possible in type theory. Okay, next up, 7. Who thinks that 7 is provable? Oh, yeah. Who's someone in the chat that knows their intuitionistic logic well? Yeah. This is actually equivalent to law of excluded middle, and this is also known as Peirce's law. And this is not provable. Again, you really only have one assumption here. This F, and you have to construct something of type A. Our F tells us we can construct a term of type A if we had a function from A to B, but we know nothing about A or B, so we don't know if there is a function between them. For example, if A is the unit type and B is the empty type, then there won't be a function from A to B, right? So in general, we can't construct an A from that data. Okay, very good. 7. Who thinks that 7 is provable? Yeah. Yeah. Okay, I got a few yeses. Yeah. So this one says if there doesn't exist an A such that B of A, then for all A, not B of A. And I can put this really quick. We give it F and A. So our assumption is that we have something. Oh yeah, sorry. Yeah, we've been saying 7, but it's 8, of course. So we have an A. We have a function from the sigma type, and we have to. Oh yeah, we have to give it a function from BA to empty type, so we can give it one more argument. Now it looks like my Agda mode stopped. Or the Agda input mode, that sometimes happens. If that happens to you, you can press meta X and then just type Agda to mode. Then we reset, but Agda mode is back on. Yeah, so I wanted to write B subscript A to sort of show that this B depends on A. So we have our A, we have our BA, and we have to produce something of empty type, but we have our F, which is negation of the sigma. So we can apply F to the pair A, comma BA. Okay. Now moving on, 9. What's the opinion on 9?
Hi, Max. My understanding is that 9 is not provable, which I hope you'll agree with. But I sort of struggle with this because structurally 8 and 9 are very similar. So I was wondering, perhaps could you give me sort of an intuition for why 9 is not intuitionistically provable while 8 is, just to wrap my head around this a little bit more.
Okay, sure. So if we're trying to prove this, first, our assumption is an F, which takes a dependent function from A to BA, so this is just a pi type really, written in Agda, and from that it produces something of empty type, right? And then we have to give something of the sigma type. So we can define here. So we have actually two things to provide. First, something of type A, and then something of type not B of whatever we put in for 2. And already the problem starts here. How are you getting something of type A from only your F? Well, one way would be if we know there is a dependent function from A to BA, then you can produce a contradiction, and from contradiction you can get something. But do we know that such a function exists without knowing anything about A and B? And that's very similar to what we had about. So on the logic side, the way to think about it is, if you want to prove there exists an A such that not B of A, you have to give a witness of that existence, which is what I've been saying type theoretically. You have to produce such an A of type A. And that is just not possible without having any assumptions on B and A. Is that satisfying?
Yes, it does satisfy my curiosity. I think I just need a little bit more training with the sort of constructive way of thinking about these things. But yes, thank you.
Getting familiar with constructive logic takes some time to wrap your hand around it. Wrap your head around it. And but this is sort of at the heart of what sets, if you're doing constructive mathematics or mathematics with constructive logic, this is perhaps the most important roadblock of one translating. So a lot of proofs, they want to produce, they want to say there exists a function such that something doesn't hold, and then they say, well, assume that for any such thing it does hold, we arrive at a contradiction, therefore there must exist such a thing. This doesn't work, right? We have to produce an object and then show that it doesn't have that property. So if you want to try and think about it more. Out, maybe that's a good comment as well. Comment out marked region is meta and then semicolon. So if I mark this whole region, I press Alt and then the semicolon, so uncomment it. I do it again, I'll comment it out. Oh, I find this very useful. Okay, and there was some question in the chats about this 9 being true in classical logic, but yeah, this has been answered with some Agda code copy pasted in the chat. So assuming the law of excluded middle, this is provable, and there's a solution in the chat if you want to look at it. Okay, last one, 10. Okay, we got one yes. Two yeses. Yeah, okay. Okay, people seem to believe that. I've found this one tricky when I learned type theory, because when you read it out, it means that if for all A there exists a B such that C of A and B, then there exists a function from A to B such that for all A, C of A and F of A. And this, if you read it naively like this, this reads like the axiom of choice, and you might have heard that axiom of choice is non-constructive. But I would say this is a point where you sort of have to take the propositions as types interpretation with a grain of salt, because this sigma really is, well, maybe you can think about it as a constructive exists, so it actually becomes provable. So let's do it. We have an F. So we have an F that takes an A and gives us something in the sigma. And then we have to provide a sigma type. So we can do Control-C, Control-R to refine. And we have to give two things. First, an A to B. So this will be something of a function lambda A to question mark, Control-C, Control-R to refine. We have to give it something of type B. Well, we have an F and an A, so we can plug in the A into F. So what do we get? We get something of the sigma type, but we want B and C over A, but we want B, so we can use the first projection. So again, this is now a dependent function, but we work completely analogously to lambda A to question mark. So we got so what we have to do now is we have an A and an F again, and we have to produce something of C of A of F of A first projection. Well, there's not much we can do. We can do F of A. This is something in the sigma type, and then we already took the first projection, so the second projection will give us the following. Well, this is actually, say, modulo the dot notation of fields of record types and the prefix notation. Okay, refine, and we're done. Yay. Okay, any questions about this? No, great. So we're not doing great on time. That's why I'm considering, so moving to the left here, skipping 3 and 4, because they sort of follow what we did up here with some of the examples. So they're really just playing around with negations. So they get a bit harder than what we did here, but yeah, really follow the same pattern. I think that maybe it'd be more interesting to look at part 2. Anyone wants to see the rest of part 1, or otherwise I'll move on to part 2. Okay. No, great. So there's solutions online. So you can prove. You can try proving this yourself, and if you struggle, look at the solutions, or and if you still struggle or have problem understanding, you can always write me on Discord. Okay. So yeah, let's do 2. So the idea is that we want to see what the equality type on bool looks like. And first exercise is sort of encoding booleans as types. And the idea is that, well, bool has 2 elements, true and false, but we also have sort of true and false on the type level, on the propositions as types. So yeah, we want to construct a family over booleans that sort of maps true to the true type and false to the false type. I'm gonna move this around. Okay, any suggestions? So we can start setting this up. Yeah, true to unit and false to empty. Yeah, exactly. That's so what we do is we give ourselves an X of type bool. We can pattern match over it. We put the X in the goal and then press Ctrl C, Ctrl C, and Agda will do the pattern matching for us. So now we have to give it a type, and we said we wanted this to be the unit type. So this is backslash B, and then a 1. Maybe I can 1. And the other one is the empty type backslash B 0. Okay. All right. And sort of we can use this family to sort of look at what equality of Booleans look like. So we want to prove the following statement. If we have two Booleans and equality between them, then we have an inhabitant of Boole's type of B, if and only if we have an inhabitant of Boole's type B prime, or sort of those are equal if and only if this is true, if this is true, if we read it as propositions as types, if this is true and this is false. Okay, any suggestions on how to do that? Path induction, yeah. So we have B prime, and P. So I use P for identities because I'm very used to thinking of them as paths. I work a lot with cubical Agda. I hope, you don't mind. Exactly. So we have to prove something of this type. And now we can do path induction by pattern matching over P. Yeah. Oh yeah, that's a P for proof of equality. That's a good one. Yeah. So we pattern match on P, Control C, and it automatically makes the B prime into B, puts a dot here to say that this is sort of an irrelevant argument. Like you can put an underscore here and it'll know that we can put a question. Can we do that? No, that's not Agda syntax. Can do it on the left. We can put an underscore here and Agda will know that this has to be the same B as here. We can do the same here. Yeah, sort of. Agda will know that those underscores have to be B. And then what this becomes is Boole's type of B if and only if Boole type is B. And this is very easy to prove. Someone wrote identity function both ways, right? Exactly, because we the way that this double implication was defined was a pair of implication from left to right and right to left, and in both cases this is just the identity function. So we can refine. We have to give it two things. First, this implication. Well, we can try this. Can't solve it. But yeah, with Control C, Control R, Control C, Control A, Agda will solve this for us. This is short for automatic proof search. Okay. This is maybe not too surprising. But using this, we want to prove the following fact. That true is not equal to false. So what we do is we give it a p. So make this window bigger. We give it a p, a supposed proof that true equals false, and we have to produce something of empty type. And yeah, okay. How if we want to, we can use our full equality characterization one. Suggestions? Yeah. That's something for later. Yeah, someone figured out a way easier, an easier way to do this, but I thought it would be instructive to see how this, because this is something that wouldn't work in cubical Agda, for example. Yeah, exactly. Someone wrote, yeah, what I had in mind. So we can use this lemma, copy and paste it, Control C, Control F to jump to the next goal. And now we apply it with true, false, and P. So if you look, these are these three arguments. So what we have is something of type unit type equals empty type, right? Or is equivalent to the empty type. So we only need the left to right implication to get us a contradiction. So this will be PR1 of this guy. So we have a function from the unit to empty, and we can plug in the one element that we have in the unit type, the star, and that's it. But as someone said in the chat, actually, Agda is very smart sometimes, and let's figure out what to do here. So we can try to pattern match on P actually. So we have proof of true equals false. And if we try to pattern match, then Agda realizes that, well, this would have to be REFL, but then sort of true and false have to be the same objects internally. And this is not possible. So we end up with the empty pattern. Okay. Some people needed to go. Thank you for your time. If you don't mind, I would go on with proving this. Yeah. If you need to leave, yeah, don't worry. I'll just carry on a couple more minutes for the interested. Yeah. Okay. So how would you proceed here? Maybe I can already get started. You give it a B and a B prime. And a by implication. This. Yeah, cases for B and B prime. Exactly. So this is also one thing that is very nice. Data types in Agda, pattern matching over several arguments at once. We type B space B prime, and then Control C will do all the pattern matching for us. And we have 4 cases. Let's Okay, let's just go through them all. Case 1, true equals true. Well, that's just REFL. True. And maybe we jump down to here. False equals false. Well, this is just REFL for false. And now the tricky part. True not equal false. No. So yeah, someone in the chat suggested the 0 elim. We can do that using sort of this result, right? No, wait, sorry, what am I doing? We give it well, we have this. And then maybe you want to explain how you wanted to use the 0 elim. Yeah, exactly. Yeah, this is sorry, I got confused. Exactly. At this point, we have to use our assumption by info here. So by info, and then take the first projection. This will give us something from 1 to 0. So we can plug in the star, the inhabitant of 1. We get something of 0. And then I think in Martin's notes, I have to look at my solutions. You should use the non-dip elim. Yeah. And so the other way works completely analogously. So if we look at here, what happened though is that sort of 1 and 0 are swapped. So we can copy paste this guy, but this will be the other way around. No. Okay, so with sort of both directions here, we sort of know we have like a way of rewriting equality of 2 booleans with our family Boole's type. Maybe this is not too surprising, but yeah, this is sort of a strategy that works for more complicated proofs as well, that you describe elements by a sort of type family, or you may call it a cover, and then sort of prove the characterization of identity types in terms of this type family. This is known as an encode-decode proof, and you'll see much more of that. This is like a very, very easy first example, and in particular, what we actually wanted to get was much easier by pattern matching, but sort of this strategy is everywhere. Okay, any questions? No? Great. Well, I'll thank you for your time and helping me with the in the chat with the solutions, and hope to see you all again, and good luck with the summer school. I'm gonna stop the recording now.